Hello everyone. This is a video where we're going to learn how to do nodal analysis for circuits that include voltage sources and specifically both grounded as well as floating voltage sources. This is quite interesting because this situation happens very often in real life. Plus, having to deal with floating voltage sources is a little bit tricky in nodal analysis. So I would like to underline the basic principles behind it and how you can deal with situations like that. So I'm going to help you through that by analyzing the circuit you see right here. Here we have something we've seen before. This is the 1.6 amp current source. That should basically provide no trouble for us. We've seen this several times in previous videos. We have this 2 volt grounded voltage source. And what we mean by grounded voltage source is that one node is basically held at 0 volts, is basically connected to ground, while the other node is one of the nodes in the circuit. And then we also have now 2 additional sources which will give us a little bit of thought. One of them is right here, which is a floating voltage source. It's floating because none of its 2 nodes, V1 or V2, are connected to ground. That's the definition for a floating voltage source. To make things even worse, this floating voltage source is a dependent voltage source, meaning its value is not something like 2 or 5 volts, but rather it depends on some other current. In this particular case, its value is 3.5 Ix, where Ix is the current right here. This will not change the way we're treating floating voltage sources, but it will add one more degree where we have to think about what to do with that dependency. And finally, we have a dependent current source right here, whose value is 2 times Vy, where Vy is the voltage drop across the resistance with a conductance of 2 Siemens. I should actually clarify that in this particular circuit, I am basically giving you the conductances instead of resistances in the elements that you see here. All right, so we're going to proceed with all the steps that we know already for nodal analysis until we come to a point where we have to think about perhaps something we haven't seen before. So step number 1 is already done for you in this circuit, is to essentially label all the unknown nodes in the circuit. And I have labeled them here, as you see, with V1, V2, and V3. Now, at first glance, you might be tempted to say that all of these nodes are unknown. However, if you pay a little bit more attention to the circuit, you will find out that V3 is actually a known node. Why is V3 a known node? Is because it is really tied to a grounded voltage source. And since I'm guaranteeing 2 volts difference from V3 to ground, I can immediately say that V3 is actually 2 volts. So in other words, the nodal equation for node 3 is a freebie. You already know before you do anything else in the circuit that your V3 will be equal to 2 volts. So you could choose to solve the circuit by keep treating V3 as a variable and all the way until the end and write the final equation for nodal voltage 3 as V3 is equal to 2 and then solve the equations. That's what you will see in the textbook. This is how we've actually chosen to solve the problem there. Or you can choose to immediately replace V3 with 2 volts and therefore solve the circuit as if you had only 2 unknowns, V1 and V2. So this is the process which I'm going to follow here in this video in solving this example. All right, now let's pay attention to node number 1. So in node number 1, I'm going to do the normal thing, as I already know. And so that means I'm summing up all the currents, leaving this node to be equal to 0. So starting from the left, by the way, V1 is exactly the same as this one here, since they're connected with a short circuit. So starting from the left, I have a 1.6 amps coming into the node. So this will be negative 1.6. Then I have the amount of current that flows out of the node through the 4 Siemens conductance. So this will be equal to the 4 Siemens V1 minus 0. That's this current. Then I have the current that leaves this node through the 2 Siemens conductor, and therefore I will have that this is equal to plus 2 times the voltage difference across that, which is V1 minus V3, but V3 is equal to 2, so I will write it as this way, plus now the current that leaves to the right through the dependent voltage source right here. Now the trouble here is that we really don't have an equation to express this current. I can't use Ohm's law for a dependent source. It's not for a dependent voltage source, I mean. It's not a current source where I could immediately know how much the current is. In reality, as we have discussed several times in the past, there is really no way to know how much current flows through an ideal voltage source. So we're kind of stuck here, and the way to address that problem is by introducing what we call a dummy variable. So in other words, I'm going to call this current I, as you will see right here. It's going to become an unknown. We call it a dummy variable or a dummy unknown because this is not something I'm truly trying to find here, but I have no other way but to introduce it and find it at the end. So I'm going to call this thing I, which, as I just said, I'm going to call it as a dummy variable. And so we'll think about what to do with this I in the future. So nevertheless, when I add I, the equation is completed, and I have now applied KCL for V1, and the result should be equal to 0. Now, if I do a little bit of cleanup here, node 1 equation will end up being 6V1 is equal to 5.6 minus I, as exactly you see right here. So this equation here is my final node 1 equation for this problem. Now, finally, I have to write down equation for node number 2. So node number 2 is right here, and I will do exactly the same thing. I will start adding all the currents leaving this node and sum them up to 0. So the current leaving the nodes to the left, it's the current that goes through this voltage source, the floating voltage source, which I just called negative I in the direction you see here. So this will be, plus I, since it's the current that leaves the node. So I will have the current I that leaves to the left, plus the current that leaves to the south, which is the current right here. And this current in this branch is dictated by the dependent current source. It's exactly the same as this current here, whose value is basically 2 Vy. So there we go. Then we have the current that leaves to the right, and this is the current that leaves through the 3 Siemens conductance. And therefore, I will basically have plus 3 Siemens. This is the 3 Siemens conductance times V2 minus V3. That must add up to 0. Now, I have a couple of things that I need to pay attention here. First of all, V3 is a known voltage, is 2 volts. Second, I need to be really careful with the direction of I. So if you look at the circuit, I called my dummy variable I to basically go to the right. So this current I is actually flowing into the node V2. So the correct way to express this is negative I, as I did in the beginning. So negative I plus 2 Vy plus 3 V2 minus 2 should add up to 0. These are essentially the 3 currents that are leaving this node. So when I clean up this equation, my equation for node number 2 now reads like this. So to summarize, doing nodal analysis for this case gave me 3 equations. V3 is equal to 2 volts. 6V1 is equal to 5.6 minus I. And 3V2 is equal to 6 minus 2Vy plus I. And so now the question becomes, what do I do? The first thing that we should worry about is what to do with a dummy variable. This dummy variable that I introduced out of necessity in both cases, nodes 1 and 2, because there was nothing else I could do for calculating the current through the floating voltage source. The way that we normally deal with this is actually by adding up the 2 equations. You will find out that one equation has the dummy variable with a negative, the other equation has it with a plus. So adding the two together will actually get rid of my dummy variable. And that's exactly what we normally do. So adding nodal equations 1 and 2 together will give me this new equation right here. Now you might say, this is wonderful, I got rid of my dummy variable, but now I have an additional problem. In fact, I have two problems. The first problem I have is that I have one equation, this one right here, but I have two unknowns, v1 and v2. So I need another equation. So I have to think about where to get this equation from. The second problem I have is that I have this vy. So this vy is the controlling variable for that source. It came into the picture because this was a controlled current source. So I have to find a way to express that. So let's tackle one problem at a time. The first thing is, let's deal with a dependent current source, meaning let's deal with this vy right here. It's very straightforward to deal with this controlling variable, vy, because all you have to do is inspect the circuit, find out exactly what vy is. So vy, according to this schematic here, is the voltage drop between the left side and the right side. So it's going to be equal to v1, which is up here, and v3, which is on the right side. So that means that vy is equal to v1 minus v3, and since v3 is known, remember we said that this is equal to 2 volts, then this result simply says v1 minus 2. And this is something that you will have to do in every single circuit whenever you're dealing with some type of a dependent source. Any type of a dependent source you have in a circuit will have a controlling variable. So you will have to go to the circuit, find out where is this controlling variable, and express this controlling variable with respect to the nodal voltages. Because remember, at the end of the day, in nodal analysis, we are finding the nodal voltages. In any of our final equations, we cannot tolerate anything else except nodal voltages. So anything else should be either known or expressed as a function of nodal voltages. When it's a voltage, like it was in our case, vy, it's relatively easy. You can immediately link it as I did here. But even if it's a current, typically by Ohm's law, you will be able to do that, and we'll do this in a minute. All right, now I dealt with the first difficulty. Now let's deal with the difficulty of the second needed equation for the unknown nodal voltages. As a reminder, I have two voltages unknown, v1, v2, and I still need a second equation for them. That second equation will be provided to me by paying close attention to the floating source that created the problem to begin with. It was this floating voltage source that forced us to introduce the dummy variable I. So this is what I'm going to pay attention to find the solution. This floating voltage source is clearly linking V1 and V2. Why? Because it's enforcing a voltage difference between these two nodes. The nodal voltage V1 is higher than nodal voltage V2 by the amount of 3.5 Ix. So I can write immediately that V1 minus V2 is 3.5 Ix. Now, that's really the equation that you need. Now, if this was an independent source, this equation would have read something like V1 minus V2 is 7, right? And I would be done. But because this is a dependent source, I have to go just one more step. And that one more step is trying to find out what is this Ix. This Ix is the controlling variable for the source. So now I have to go back to the circuit and find out where is this Ix. The Ix is right here. It's really the current that flows upwards from the current source, the 2Vy current source. And since Ix is in the opposite direction of 2Vy, I will express this Ix as negative 2Vy. So putting everything together will give me that V1 minus V2 is equal to negative 7Vy. So I basically I'm done because Vy is known. Vy is right here. So I have now two equations. I have the equation right here, which will become immediately useful once I replace that Vy is equal to V1 minus 2. And I have this equation right here, that V1 minus V2 is equal to negative 7 Vy, which will become again immediately useful once I express Vy as V1 minus 2. So two equations, just two unknowns, V1, V2, I can go ahead and solve them using either the matrix form or substitution or any other methodology you want, and you will find out once you do that V1 is 1.8 volts, V2 is 0.4, and of course V3 is 2, which is what we already knew. So this is a fairly long example because I went step by step in addressing each of the difficulties that you may encounter. But I think it's a really good example that demonstrates everything that you may encounter, or almost everything, I should say, that you might encounter in a relatively complicated circuit. It had floating sources, it had dependent sources. So before I finish, let's quickly review what we learned from here. So the first thing that we learned is that whenever you have a grounded voltage source, you know the node that is tied to this source. In this case, this was tied to the node V3, and therefore we knew what V3 is, 2 volts. The second thing that we learned is that when you have a floating voltage source between two essential nodes, in this case it was V1 and V2, you must introduce a dummy variable to express the amount of current that flows into that source. This is important because really you don't know this current. There is no equation for you to think about here. Now, there are other methodologies you can equally well deal with this. For example, in other textbooks, there is the concept of a supernode, which essentially does the same thing with a fancier name. In other textbooks, you will also find something called modified nodal analysis, that is a technique specifically made to deal with floating voltage sources, and essentially does exactly what we did right here. But I really don't think you need this type of fancy names. All you need is a clear mind and a logical approach to things, and you can very quickly get the solution as we're discussing here. The third and final thing we learned is that whenever you have a dependent source, and here we ended up having two, you will at the end of the day write an equation that will include the controlling variables. Ix was one controlling variable here, Vy was the other controlling variable there. You will have to go back and write each one of these controlling variables as a function of the nodal voltages, because your final equations must include nothing except for nodal voltages. So thank you for watching this video. I hope you will be able to go and do it yourselves, get the same results, and we'll see you next time.